Okay, so I wanted to put together what it's hopefully going to be a pretty short and maybe really to the point video going over the last homework problem for both Physics C and Physics 1 in homework set 05A, which deals with uniform circular motion. And what this homework problem deals with for both classes is the idea of a banked curve. And a banked curve, or at least in the physics sense, is taking a look at a car making a turn around a curve, but the road that it's taking that turn on is actually inclined at some angle theta. So it's a stretch of road that's not perfectly horizontal, but we're still looking at a car as it's making a turn on that stretch of road. And so to kind of visualize this, because I think both homework systems don't do the best at really explaining what this looks like, this is kind of what we're looking at. Big old bus. It's moving at what we're going to take as being constant speed along this banked curve. And as it's moving at constant speed in what we will model as a circular path, it still is exhibiting uniform circular motion. The only difference is the forces at play, because of this incline, is going to look a lot different. So I'm making one just broad video for both AP classes, but pay close attention because I think in the Physics C one, there is no friction, but in the Physics 1 problem, there is friction that you're asked to solve for. So I'm going to kind of set us up in this video just the concepts that are going to allow you to solve this problem. I'm not going to necessarily work you through every single step and plugging in every single number, but it's just about concepts and how you can visualize a problem like this so that you can get started. Okay, so here's what we would do. We would kind of draw this out, and I think this is how both homework systems visualize it. Here's your banked curve, and here is the car traveling on that banked curve. Now, we're kind of looking at this from behind, right? So here's my car. We're looking at this from behind, and this is my angle of inclination theta. And so we would see that, all right, here's my banked curve, and the car is traveling on it. It's going to kind of make a turn like that. And we've seen that cars making turns, we can effectively model as a car traveling through at least a portion of uniform circular motion. And what's really important in uniform circular motion is the following. We can have all kinds of forces acting on the object. We kind of saw that with the Ferris wheel. We had two forces acting on me as I rode around the Ferris wheel, but what we always had to have was a net centripetal force, or a net centripetal acceleration. And if I'm looking at this car, as again, I'm imagining it's traveling in a circle something like this on this banked curve. Well, the center of its circular path would be somewhere over here. And so here's what we get. I must, by definition, by all the things we talked about in setting up UCM, I must have a net acceleration that points towards the center of the circle, a centripetal acceleration. And this is how you're going to have to go through and solve this problem. The best way to do this is with the centripetal acceleration viewpoint, right? We've talked about the two ways of solving UCM problems. The best way to do it is right here. Understand that there's a net centripetal acceleration for anything moving in a perfectly circular path. But what gets really tricky here, I have to call back on some knowledge that we talked about back in dynamics whenever we first introduced inclined planes. Now, we really only spent a day or two on inclined planes because we set the foundation for you to use Newton's second law so well that all we change in inclined planes is, all right, here's our standard coordinate system where positive y points up, positive x points that way. All we're doing now is we're just kind of tilting that to align it with the inclined plane. But if you look back in your notes, I said that the reason we are going to tilt our axes in problems involving inclined planes back in dynamics was so that we could get all of the acceleration to be in just one direction. Because in a more standard inclined plane problem, we would maybe put an object at the top of the ramp and let it slide down the ramp. And we notice that, okay, the acceleration as it slides down the ramp, it points down this way. So I wanted to pick a coordinate axis, something like this, where this is positive y, this is positive x. We picked that so that that acceleration, which again would point down that way in a standard inclined ramp problem. All of that acceleration is now just in the negative x direction. And then we went about, solved everything kind of like normal, just with a new tilted coordinate axis. But I want you to again think why we did that. We tilted our axes so that all of the acceleration of the object would be in one direction, just one direction. But in dealing with a problem with a circular path, uniform circular motion, we get that we must have a net total acceleration pointing towards the center of the circle. And so with the way we've drawn this and the way it draws it for you in your homework system, this is what we would have to have. And if I think about using this coordinate system over here, this tilted one, With this type of centripetal acceleration, well, look at what I did. If I were to draw my acceleration vector over here, it's not all the way in the x direction, it's not all the way in the y direction, it's in some combination of those two, and that's a problem. So for a banked curve problem like this, because we need to pick a coordinate system such that all of our acceleration is just in one direction, we are actually not going to tilt our axes. And what that does for us is with this acceleration vector, now I would have, again, if my negative x direction is over this way, all of my acceleration that this thing must experience to maintain its circular path is pointing just in the negative x direction. It's all in just one direction. It's not some combination of the y and x, it's just all in the x direction. And so that's going to complicate problem solving just a little bit. And let me kind of get you set up here to actually deal with a problem like this, okay? If I were to think about a free body diagram for what I have drawn here, for this object moving in a constant speed at a constant circle, here's what the free body diagram would look like. Well, it's always helpful to kind of draw a dashed line when dealing with ramps or inclines just so we can easily see where the surface is to help us draw our normal force. And so on this car, it's still going to have a force of gravity acting down. It's going to have a normal force, well, normal to the surface, or 90 degrees to the surface. And so we get something like that. That would be my normal force. Now, what we had to do back in inclined planes, because of our weird tilted coordinate system, was we had to split our force of gravity into two components. But now, remember, we're sticking with our normal coordinate system like this. So now, this actually isn't going to have any components. It's just in the negative y direction. What is going to have components now, however, is going to be our normal force here. And again, that can be kind of tricky to conceptualize, pretty tricky to deal with without actually seeing it. So with my standard coordinate system, this vector, it points up and to the left, meaning it's going to have a y component, f in sub y, pointing up, and then it will have an x component, f in sub x, pointing to the left. And you're going to absolutely need to set up some stuff here to solve for probably both of these. And if you want to do that, well, you need to know, this makes a right triangle, but you need to know at least some information on one of these angles here. And the way the geometry works out, feel free to prove it to yourself, but the way that the geometry would work out here is whatever angle you have your incline at, right, theta, the way I've drawn it, this angle right here for your normal force right triangle will also be theta. And so you could use that to solve some information here. Now, this is kind of what it looks like for Physics C. Physics 1 takes it another step, and it's asking you about the coefficient of friction that you need to have in order to keep this thing up on the ramp, keep it moving in its perfect circle. We have to think about, okay, I have an additional force now on my free body diagram, a force of static friction. That's the one that allows us to make these turns. But I have to think about which direction that's going to point. And a kind of easy way to visualize that is imagine that we were looking at this car moving around the circle, again, like this, right? Moving like this. But imagine which way that force of static friction would be pointing if we were on flat level ground. Well, if the car is right here on flat level ground, then we have the force of static friction would be pointing in towards the circle. It's what's allowing us there to move in a circular path. But all we're doing in this problem is taking that same concept, when we need static friction to allow us to safely make the turn, we're just taking it and we're inclining everything. So now, your force of static friction, it's still pointing along the surface, right? It's an interaction between the surface and the wheels, but it's actually still going to be pointing as close as it can to the center of the circle. So I have a force of static friction down this way. Again, this is only for the AP 1 question. The AP CE question does not deal with friction at all. It's a frictionless banked curve. And this brings up another issue, and this is, again, probably a pretty mean problem. But what do you notice now about the force of static friction? With our coordinate system, it's not all the way in the x, it's not all the way in the y, it's in a combination of the two. So our force of static friction, because we're choosing to stick with this coordinate system, because it makes the most sense, we have to draw that it also has components. So we have F sub S sub x, great. because this thing points to the left and down. We have a component in the y direction pointing down, f sub s sub y. And hopefully here, the trigonometry isn't too terribly complicated, but we would get that the angle theta that we have for our incline would also show up right here. Just making sure, yeah. And so you're going to actually have to solve all this information, a lot of this information, to set up and solve for the coefficient of friction. Now, this again, I'm really just getting into the AP1 question now. So APC, you should just take this information here and start trying to solve with that. But for AP1, here's what you need to think about. It asks to find the minimum value of the coefficient of friction such that this car is able to make this path. Again, you have all kinds of numbers, but it's asking you to solve for the minimum value of the coefficient of friction. I'm going to give you a little bit of hint to get you started here. When doing that, because we know that typically we write F sub s as less than or equal to mu sub s times the normal force, in this problem, you're going to effectively treat F sub s as being equal to mu sub s times the normal force. And the reason we're doing that is we're just basically saying, all right, this is when we have the static friction is at some maximum value, right? Because when we have this, this is our maximum value, right? The force of static friction can be under this, or at its greatest value, it can be equal to this. So this is saying we're dealing with the maximum value of static friction. Now, we're basically kind of working around this so that we can use this as an equal sign. Here's what we're saying. We are dealing with the maximum value of static friction that can be sustained by the minimum value of coefficient friction. So we are looking at, with a given coefficient of friction, the maximum value of friction that it can sustain. Again, don't get too caught up in the weeds on that. Maybe think about it for a second. It's just basically allowing us to set F sub s as equal to mu sub s times the normal force. And so, how could you go from here? Well, let's not forget, when doing the centripetal acceleration viewpoint, we have to now apply Newton's second law. We've drawn a free body diagram, we have to apply Newton's second law. And because our acceleration, our centripetal acceleration is in the x direction, a good place to start here would be applying Newton's second law in just the x direction. And see where you can go from there. It's going to involve a lot of trigonometry, a lot of solving for things up here to solve for this, then plugging in here. It's a very complicated problem. So I've given you an idea of kind of how to draw it out, how to start. Now you're using concepts of circular motion to go through and hopefully solve. Again, if you were just completely lost and still need help, reach out to me. We can get you started, get you some help. But this is kind of a conceptual video as to how you can set up a problem involving a banked curve.